All right, we're back. So looking at so essentially where we're going in the notes right now is looking at different acids and trying to compare them as far as how acidic they are. So we have three acids here. We'll just call them A, B, and C. And I want you guys to just get a overall estimate right now of which one you think is the strongest acid. You pause the video. You're back. All right, so you have your estimate. So what was that based on? Well, hopefully you're going back to the same idea. The strongest acid, what does that create? The strongest acid has the most stable conjugate base. And how can conjugate bases be stabilized? We saw if we compare a carboxylic acid to an alcohol, delocalization of the charge stabilizes the conjugate base of the carboxylic acid. That makes that conjugate base of the carboxylic acid more stable. That makes the starting carboxylic acid more acidic. But all of these have that same resonance delocalization. The oxygen has the negative here, negative here, negative here, but we all know that it's also shared on that oxygen there as well. We could draw those resonance structures if we wanted to. So the real difference here is how does this group impact it? Well, we have a chlorine versus just a CH3 versus a T-butyl group. So how does that impact the acidity of the acids? Or even more, the way we should be thinking about is how do these somehow stabilize or destabilize that negative charge? So you can think about that like negative charge is something that is not very stable. We don't want things to be charged. So something that decreases the amount of charge should stabilize it or delocalizes that charge. So decreases, delocalize. Delocalizing or decreasing charge stabilizes it. So we'll just say more charge buildup is bad. Charge buildup is bad. It's destabilizing. So how does this chlorine impact that oxygen? Well, chlorine's electronegative. Way back in chapter 2, when we really talked in depth about acids and bases, it does something that we called induction. It's pulling electron density toward it through the sigma bond. So it is inductively withdrawing. That puts a partial negative there and a partial positive here. This partial positive gets transmitted down the backbone of the organic molecule. So there's a partial positive here. There's another one here. It's a little bit smaller, but it goes to that next carbon. So how does that partial positive impact the negative? Well, the negative wants to delocalize, and it's going to delocalize better if it can put that electron density onto a partial positive. Essentially, this partial positive here, the partial positive, stabilizes the O minus. So that actually makes it more stable. Okay, well, if we compare that to this, well, we don't have the chlorine there, so that's obviously not doing it there. Well, how does that compare to a T-butyl group? This chlorine, the chlorine is an electron withdrawing group. What is this tert-butyl group? We would call this group, is it electron withdrawing or electron donating? Boop, you pause it, thinking about it. What is it? It's an electron donating group, right? This is an electron donating group. It donates electron density through hyperconjugation. Remember, hyperconjugation is kind of a lower form of conjugation, but it is still something that lends negative charge. So essentially we have negative charge being pushed toward a negative charge. So here we're adding a partial minus. A partial minus is close to an O minus. That is destabilizing. So way back to the beginning, Which of these is the most acidic? The strongest acid is linked to the most stable conjugate base. Chlorine stabilizes the negative charge. This destabilizes the negative charge. This is the most stable conjugate base, so this is the strongest acid up here. And this is the weakest acid down here. That kind of puts in that induction piece, that hyperconjugation piece. If we have negative charge being added to a negative, that is a destabilizing interaction. If we have a partial positive next to a negative, that is a stabilizing interaction. So we'll see that being pretty important throughout this chapter. All right. All right, we're back with another one. So which of these is the stronger acid? The way I have it written in the note packet is, well, which of these is the more stable conjugate base? Because whichever one of these is more stable would mean that it came from the stronger acid. So pause it for a moment, take 30 seconds to a minute to think about that, and then come back. So boop, you did that. Now you're back. You've made your guess. Okay, so the more stable conjugate base is going to have less charge buildup. It's going to have a partial positive stabilizing the negative charge on the oxygens. So both of these things do induction, right? So what's the difference? We have a chlorine 2 carbons away from the carbonyl, and here we have a chlorine 1 carbon away from a carbonyl. Both of those chlorines are going to do induction, but when we think about it, the partial positive that's attached to the chlorine is going to be a certain size on the carbon that's directly attached. And remember, the size of that partial positive gets smaller and smaller the farther it gets away from that chlorine. So here we have a smaller partial positive, smaller partial positive. And now we're actually on the carbonyl carbon. We're able to stabilize that negative by having that partial positive right next to it. Versus this one here has an additional carbon to go to, so that partial positive is even smaller when it is actually next to the negative. So this larger partial positive does a better job of stabilizing that negative charge. So this is the more stable, conjugate base. So that would mean that this is the stronger acid. And why was that? Again, that's because induction fades with distance. We have a larger partial positive adjacent, so right next to the O minus. So we want positive to balance that negative, and we get it more here than here because of that distance effect. All right, we're going to do another one. We are back at it with another example. Which of these is the stronger acid? Again, how do we do that? Figure that out by looking at the conjugate base. So we have the conjugate base here versus the conjugate base here. Okay, so which of these conjugate bases is more stable? The more stable one came from the stronger acid. So decide on your own. Boop, you paused it. You're doing that right now. You're deciding on your own. You're back with me. Which of them is the more stable conjugate base? This one's the more stable conjugate base. This is the more stable conjugate base. It's from the stronger acid. Why was that? We know induction stabilizes negative charges. We have a chlorine here that has the partial minus, partial plus here. It comes over here to partial plus. Well, how does that differ from this one? Well, this one we have 2 chlorines. Both of them are going to have about that same size, and I'm trying to do it roughly to scale. that same size is the same as those two, but that means that there are two chlorines pulling away from that one carbon. So instead of this partial minus being balanced by the same size partial positive there, there's going to be even a larger partial positive on that carbon right there. So this partial positive is larger than that partial positive, which means that the partial positive relayed to the next position is again going to be larger. So this one is smaller than that one, but it is bigger than that one. So essentially, larger partial positive next to the negative, that's going to be a more stable conjugate base. So breaking that down, if there are more electronegative atoms, so we should put En for electronegative, more electronegative atoms, there's more induction that would occur. And if there's more induction occurring, that means that the partial positive is going to be larger. So that means a larger partial positive if there's more induction. Yeah, we're going to talk more about acid-base chemistry continuing.